In this video, we are going to explore how computers perform addition and subtraction of numbers, starting from the very basics, and then we will go on to design our very own arithmetic circuit. Let's get started. To convert a decimal number to binary form, follow this procedure. Perform successive division on the decimal number, dividing by 2 in each case, and writing down the remainder for each division. Keep dividing until your quotient is 0. Write down the string of remainders that you obtain, starting from the last one and moving to the first. This gives you the equivalent binary value of the decimal number in question. To convert a binary value to its decimal equivalent, label all your bits with powers of 2, starting with 2 to the power of 0 at the rightmost bit. Move leftwards, labeling each bit with the appropriate index until you reach the leftmost bit. Next, multiply each index by the corresponding bit and add all the products to obtain the corresponding decimal value. Simply put, add all the indices corresponding to ones in your binary word, since those that correspond to zeros will be eliminated once you perform the multiplication. Now let us move on to binary addition. To add binary numbers, follow these rules. First, 0 plus 0 is 0, and 1 plus 0 is 1. Second, 1 plus 1 is 2, which in binary form is written as 1, 0 and read as 0, carry 1. Lastly, 1 plus 1 plus 1 is 3, written as 1, 1 in binary form and read as 1, carry 1. Let's look at an example. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0, carry 1. 1 plus 1 plus 1 is 1, carry 1. And lastly, 1 plus 0 is 1. We do not need to perform binary subtraction, because computers perform the subtraction of decimal numbers by adding binary values, as we shall see now. To subtract one decimal number from another is similar to adding a negative number to another number. To achieve this with computers, which can only use ones and zeros, we need a way to represent negative decimal numbers in binary form. One way is to use the most significant bit as a sign bit, with 0 representing a positive number and 1 representing a negative number. This is called the sign magnitude approach. However, it requires complex circuitry to implement, so the favored method is the 2's complement method. The 2's complement involves 3 stages. First, convert the magnitude of your negative decimal number to its binary equivalent. Next, flip all the bits in that binary word, meaning 1s turn into 0s and 0s turn into 1s. What you obtain is called the 1's complement of the original binary word. To get to the 2's complement, add 1 to the 1's complement, and you are done. The 2's complement is the binary equivalent of a negative decimal number. To subtract one number from another, simply add the 2's complement of the negative number to the binary equivalent of the positive number. This is equivalent to adding a negative number in decimal form. Now that we know how addition and subtraction operations work in binary form, we can implement circuits that will perform these operations in our 8-bit computer. Let us begin with a simple circuit that adds 2 bits and outputs their sum and carry bits. We shall start with a truth table for adding all the possible values that inputs A and B can assume. For each case, the sum and carry can be obtained by following the rules of addition that we have already established earlier in this video. By looking at the truth table, we can see that S is high when A and B are different, which is the property of an exclusive OR gate. You can learn more about logic gates on this channel. I have put a link to another video down in the description. So, S is the output of an exclusive OR gate to which A and B are the inputs. The Boolean expression for this is written as follows. This is the Boolean operator for the exclusive OR gate. For C, the truth table resembles an AND gate because it is only high when both A and B are high. So, C is the output of the AND gate, in which A and B are the inputs. The Boolean expression is written as follows. The dot is the operator for the AND gate. This circuit is known as a half adder. For us to be able to add binary words, we need a circuit that can account for the carry bit as well, meaning our circuit has to take in 3 bits instead of 2. Here is the truth table for this adder. Again, The sum clearly represents an exclusive OR gate for these three inputs because S is high whenever there is an odd number of ones for the inputs. For the output carry bit, the corresponding circuit may not be that apparent. To deduce it, we can resort to using a Carnot map. If you are not familiar with those, I have linked to another video down in the description. This is the 3-input K-map for the output carry bit. After obtaining our fundamental products, we can deduce the Boolean expression for it. This translates to 3 AND gates connected to an OR gate, which then gives us the output carry bit when adding any 3 bits. This entire circuit is called a full adder because it takes into account the carry bit. Using our half and full adders, we can now design an arithmetic circuit that can add and subtract numbers. Let us begin with a circuit that can add 4-bit binary numbers. From what we discussed on binary addition, we first add the 2 least significant bits and work our way to the left. The first addition only has 2 bits, and thus will only require a half adder. Successive additions will also include a carry bit from the previous addition, so we will have to use full adders for the rest of the bits. This circuit is what we call a 4-bit adder and can correctly add any pair of 4-bit binary numbers. We also want our computer to subtract numbers, and to achieve this, we have to alter this circuit. First, let us replace this half adder with a full adder, and then pass the binary word to be subtracted through a 4-bit inverter. I will go over how the bit inverter works in the next video. Lastly, we add a sub-control signal that we connect to both the inverter and this full adder. When performing subtraction, switch the sub-signal to a high state. For the bit inverter, it will cause all the bits to be flipped, thus yielding a 1's complement. Since the high sub-signal is also an input to this full adder, this is similar to adding a 1 to this 1's complement binary word to produce a 2's complement, which is then added to the other binary word to give us a difference of any 2 numbers that we choose. When sub is low, the bits are passed through the inverter without any changes, and a 0 is added here. So this will simply perform normal addition on the 2-input binary words. In one of the upcoming videos, we will implement this theory in our simulator, so stay tuned for that one. That's it for now. Thanks for watching.